We are joined by NASA astronaut Drew Feustel. Drew, thank you so much for being here today.
My pleasure.
Before Drew became a NASA astronaut, he studied seismology. Drew, what does that mean?
I specialize in the study of earthquakes and more specifically in mining seismology, so looking at seismic activity that's induced by mining activities.
Drew, one of the things we love to do here on STEM in 30 is science and food. So Marty, I'm going to hand you this awesome blue
Yes, we
icing.
have incredible blue icing today that's going to represent our mantle, and then we've got graham crackers that are going to represent the crust. And Drew, we're going to let you do the honors here.
Okay.
So we're going to put a little layer of mantle down.
Yeah, okay. I'll take on that task. And you know, the mantle is pretty deep in the Earth's crust. The Earth is a very large planetary body. I know that might be enough for now. That could be the first layer. The crust can be as thick as up to 100 kilometers thick in some areas, which is really pretty thick. Let's say that's the mantle down there in the crust, and then let's pretend also that there's some layers in between the crust. There's some soft layers and some hard layers, and that'll just help to stick all these together.
Okay.
We'll make quite a kind of a mess here.
That's what we're good at.
So there's the crust. I think we're all familiar with earthquakes, right? It's when the Earth's crust can break or crack, and it happens for a lot of different reasons. And the way we typically see evidence of earthquakes or seismic activity or plate movement is that we see the edges of the crust boundaries.
Okay.
And we can see that from space too. And I don't know if I can, I probably should have broke them all individually, but if we break all these layers and then sort of spread them apart, this is what we typically see when we're either looking from space or out on a geologic field excursion. We see this layering in the crust.
What happens when if they pull apart and then they push back up like that?
Yeah, so we also have areas that we call, for example, subduction zones. So we get ocean crust diving under continental crust, and so sort of like you explained, but usually oceanic crust is a little thinner, so we'll put one layer there and then we'll put a continental crust here, and then what you get is mountain ranges building up, and right somewhere internal to where the subduction zone is, you'll get volcanoes. So Mount Rainier, all the volcanoes along the west coast are because of the subduction zone. That oceanic crust is diving beneath the continental crust, creating a lot of heat, and then you get mantle material that kind of makes its way up to the surface and pops out on top, and then that causes volcanoes to form up on top of the oceanic crust.
But every once in a while, it moves real hard and real fast, right?
It does.
What's happening there?
So that's different. That's where we have a crustal boundary, like a transform fault or something, where you get two continental plates that are bound together, but a weak zone in between. And what happens is they build up some stress, and there's some stiction between those. There's friction, right? And eventually that the force that's pressing on the plates is greater than the force of friction holding them together, and they'll snap and they'll slide. And you get these transform faults or slip faults, and that's when we can have problems and see a lot of devastation due to those plate boundary movements.
Awesome.
So it's a good idea to try to predict those. That's where seismology comes in, because we can put sensors in the ground, microphones that can listen for those sounds and listen for what we call precursors to that activity.
Awesome.
Save lives.
Great science here and pretty delicious.